a brief review of Lagrangian functions. I'm glad you're all in such a good mood. Then, Ian, I'll get to your question next, okay?
Ian doesn't have a real
I don't
question.
have a real question. It's Friday.
Okay.
The sun is shining, and I actually enjoyed the
Well,
for a second. I was like,
we can pull the blinds if you like, so you don't know that the sun is shining.
It's closing the day, the sun is shining, things are clean.
Well, Ian, just think, had we taught 619 the way we've been doing in the past, you would have had not only a morning session, but an afternoon session.
and we'd be done by now.
If yes, but would you still be alive? That's right, exactly. Okay, so let me just briefly review constrained optimization problems. Suppose the problem is this. You want to maximize some function of x and y, subject to the constraint that g, some function g of x and y equals a constant. Okay, that's the setup. Now, this technique also works if you're minimizing the value of a function. But for right now, let's assume we want to maximize the value of the function. Then Jacob, our Lagrangian function is what?
Is big Z
Right.
equals f of xy.
Right.
Plus lambda
Right.
In parentheses we do c minus gxy.
Right. Okay. This little f is the objective function, the thing you're trying to either maximize or minimize. In this case, maximize. Lambda, we call that our Lagrange multiplier. Okay. So this is the objective function. This thing right here is called the Lagrange multiplier. This is our constant, C. And this is our constraint function, this thing G. All right, so what are the first order conditions that you must satisfy in order to maximize your objective function?
d dx d dy d lambda.
Okay. All right, let me write it this way. Z sub x. This is the partial derivative of z with respect to x. Okay. And by the way, let me back up a second. What did you call this whole thing? Your capital Z is called the, or this whole thing is called what? What kind of function? Lagrange function. Okay. And let me just emphasize this one thing. This capital Z is the Lagrange function composed of the objective function plus lambda times C minus G. This Lagrange function, this capital Z, is a function of three variables, x, y, and lambda. Those are the three variables. This Lagrange function introduces the Lagrange multiplier as an additional variable in the Lagrange function. Notice the objective function only is a function of x and y. But the Lagrange function also includes this variable lambda. Okay. So z sub x is the partial derivative of z with respect to x. And that will simply be f sub x, the partial derivative of your objective function with respect to x, minus lambda times g sub x. You set that equal to 0. Okay. When you differentiate z with respect to x, you get a partial f partial x here, minus lambda times partial g partial x. Okay. And then you take the derivative of z with respect to y, and you get f sub y minus lambda g sub y equals 0. And then finally, z sub lambda, partial derivative of z with respect to lambda, is obviously just c minus g, which is a function of x and y. And as a result of satisfying this first order condition, you're guaranteeing that the constraint is satisfied. Okay. If you just bring this g over to the right, notice what we would have, g equals c. Okay, so this condition just guarantees that the constraint is exactly satisfied. Okay. So the way you solve these, the easiest way to solve these is just to take these two conditions, solve for lambda. And you get lambda equals f sub x divided by g sub x. And from this equation here, from this first order conditions, you get lambda is f sub y divided by g sub y. Okay. Now, generally, when you solve this equation right here, you will get some relationship between x and y. Say y is equal to 2x, for example. Then you use that information and you go back to this equation, and that will generally allow you to solve for x and y and lambda. Okay, or at least from this one you'll get values for x star, y star, and then you go back to here and you solve for lambda. Okay. But those are, Jacob, the first order conditions. Okay. Now, you want to check to make sure that you have, say, a maximum or a minimum for a different problem. So here are the second order conditions. These are sufficient conditions that will guarantee a maximum or a minimum. You look at this bordered Hessian, and it's written this way. And the bordered Hessian is just this. It'll be 0, g sub x, g sub y. First column will be 0, g sub x, g sub y. You have the same border here. That's the border. And then the remaining terms are capital Z sub x, x, capital Z sub x, y, capital Z, y, x, capital Z, y, y. And basically what this is, it just guarantees that the second order total differential of your objective function will be negative definite for all values of dx and dy that satisfy the constraint. So it's the same idea as before, at least for a maximum. Okay, and it just works out to be, this is the condition for the second order total differential to be a negative definite. And actually for a maximum, you want the second order total differential to be negative definite. So this sufficient condition is that this be positive. Okay, for a maximum. So for a minimum, you just reverse it. For a minimum, you want that second order, you want this bordered Hessian to be negative. Okay. All right. So so if you have your constraint function, you just take the partial derivative of it with respect to x, and you get g sub x. Take the partial derivative of this with respect to y, you get g sub y. That's what goes in your border here. Now z sub xx, z sub x was part of your first order condition. Let me write that down again. Z sub x was just this. Just take the derivative of that with respect to x, and you get z sub xx. So that would be f sub xx minus lambda g sub xx. Okay. That's what goes in here. Z sub xy. Take the derivative of z sub y with respect to x, and you got that. So you just plug in all those terms and see if that bordered Hessian is positive. If it is, that guarantees that you have a maximum. If it's negative, it guarantees that you have a minimum.
If it's guarantees that we have a minimum, does that guarantee that we also have a cornerstone solution?
No.
Okay.
This will be, if it's, it'll generally be an interior solution. We'll talk about corner solutions later.
Okay.
Right now, we're dealing really with interior solutions. If you satisfy the first order conditions, then that'll generally guarantee an interior solution, not a corner solution. But we'll talk about corner solutions later.
What I mean is, if we have a minimum, does that mean that there will be a cornerstone solution? Not that what we saw.
No. See, for some problems, we'll want to minimize the objective function. Maybe you want to minimize the cost of producing a given level of output. So you would satisfy the first order conditions. And then you'd check the second order conditions. And if you satisfy the first order conditions, that'll generally give you an interior solution, not a corner solution. But we'll talk about corner solutions later.
Okay.
So positive value for the bordered Hessian guarantees a max. Negative guarantees a minimum.
Are you talking about the determinant of the bordered Hessian?
Right. The determinant of the bordered Hessian. You're right. Exactly. Okay. Would you like me to go through one more simple example, or do you have it?
Well, we should ask
Do you understand
who wasn't here for the last class period.
who wasn't here last?
Greg, because he doesn't have that
Okay.
class.
Okay. Well. Oh. Okay. Well, Gray's a math major, so he can handle it. Now, Gray, would you like me to go through a simple example to illustrate this?
Sure.
Okay. All right. Okay. Actually, let's do an example that we had done earlier in 319, but we had not done it using constrained optimization. We'd done it a different way. The problem is this. Gray, you'll remember this problem. And Zach, you may remember it too, though it's been a while since you took 319. Certainly, Brianna will remember it. You have some fencing in your garage, Gray. You remember this, okay.
Right at the end of the
64 feet of fencing in your garage. Jacob, you remember this problem?
Yeah, I can solve it right now.
Okay, all right, okay. Well, here's a bird's eye view of your house. Okay, you can have a rectangular house. This is a bird's eye view. And you have 64 feet of fencing. And what you're going to do is use this fencing. Now, your garden, you've decided you want your garden to be rectangular in shape. And your garden is going to use one of the sides of your house for one of the sides. Okay. So here is the fencing. This is a width. We'll call this the length. And here's the other width. So you want to maximize the area of this garden. So how do you set this up as a Lagrange function? You want to maximize area subject to the limitation that you have on fencing. And if you have 64 feet of fencing, what is our constraint going to be?
2W plus L equals 64.
Okay, 2,
W.
yes, 2.
Equals 64.
Okay, that's very good. And Ian didn't even take 319. And he knew the answer right away. Okay. Okay, good. So our constant here is 64 equal to 2W plus L. Okay. Now, what is the area equal to?
Length times width.
Yes, okay. W times L. So W times L, that's our objective function. That's the thing you're trying to maximize. W times L. Subject to the constraint that you only have 64 feet of fencing. 64 equals 2W plus L. So now, who can tell me what the Lagrange function is?
WL plus lambda.
Okay, first we start off with what? What's the dependent variable? Yes, capital Z. So let's start with capital Z equals WL. Yeah, that's our F function.
Plus lambda parentheses 64 minus 2W minus L.
Right. Exactly right. Right. Exactly right. That's our Lagrange function. Okay. So how do we solve for the optimal values of W and L? Well, first we look at our first order conditions. And our first order conditions are as follows. I have W first, so let's do Z sub W. Z sub W would be L minus, we're doing W, so it's minus 2 lambda. And now Z sub L would be W minus lambda equals 0. And Z sub lambda would just give us our constraint, 64 minus 2W minus L equals 0. Okay. Now, the easiest way to do this is to take these two first order conditions and solve for lambda. So from the first one, I get lambda equals L divided by 2. Okay. From the second one, if I solve for lambda, I get lambda equals W. Okay. So in other words, we have, this is the relationship between W and L. Or let me write it a different way. L equals 2W. We just multiply this part by 2. We get L equals 2W. Now, we got the relationship between L and W. We go back to our constraint and just substitute in here. In our constraint, we have 64 minus 2W. But L is equal to 2W, so I could say a minus another 2W equals 0. Or in other words, 64 equals 4W. Divide by 4, and you get W. We'll call it W star. We think it's the optimal value. 64 divided by 4 is 16, isn't it? So our L star, remember L is equal to 2W, would be 32. Okay. So if you want to maximize the area, it looks like, looking at just the first order conditions, this should be 16, that should be 16, and this should be 32. But we really only looked at the first order conditions. We really should look at the second order conditions to make sure that we have a maximum. In this case, we're changing our notation a little bit. Before, the two variables were x and y. Now the two variables in the objective function are w and L. But that's a slight change. So our bordered Hessian should be this. But let me just slow down for a second here. What is our g function? Our constraint function. Right. So what is a g sub w? 2. What is a g sub L? 1. Okay. All right, so we got that. And our bordered Hessian. Oh, you know what we should do? What I forgot to do over here? W and lambda are the same. So our lambda star value is the same as W, which was 16. So let's make note of that. Okay. The determinant of our bordered Hessian is this. It's going to be 0. We're letting W come first, so this is G sub W, G sub L. G sub W, G sub L. This will be Z, WW. This will be Z, WL.